Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the Introduction to Magnetic Properties, which is in the fourth module, Magnetic Properties and Superconducting Properties. So, here in this session, I'm going to talk about the Introduction to Magnetic Properties. Here, we are going to cover the topics, introduction of magnetic materials, and then we are going to see some of the basic definitions, what is magnetism and magnetic dipole, magnetic flux, intensity of magnetization, magnetic induction, magnetic field strength, what is magnetic susceptibility and what's the formula for magnetic susceptibility, and magnetic permeability, and what about the magnetic permeability of free space, that is mu naught, and relative permeability, the relative magnetic permeability. Then we are going to see the magnetic moment, then what are the textbooks that have been referred for this session. So for this session, clearly written what are the reference books I have verified for this topic. Uh, Introduction. So in this introduction, so the magnetism is one of the phenomena by which materials exert attractive or repulsive forces on other materials. So magnetism is one of the phenomena. So one of the phenomena by which materials exerts attractive or repulsive forces on other materials. So some of the materials that exhibit easily detectable magnetic properties. Some of the magnetic materials exhibit easily detectable magnetic properties, such as nickel, iron, cobalt, etc. So, however, all the materials are influenced to greater or lesser degree of magnetism by the presence of magnetic field. So, uh, all the materials are influenced by or are influenced to greater or lesser degree by the presence of magnetic field. So, any material, any magnetic material that can be magnetized by the application of external magnetic field is called the magnetic material. So any material that can be magnetized by the application of external magnetic field, so then we call it as magnetic material. That material called it as magnetic material. So magnetic materials plays an important role in industrial and scientific research fields. So magnetic materials plays an important role in industrial and scientific areas. So the magnetism of the materials is mainly due to the interaction of uncompensated magnetic moments. Uncompensated magnetic moments of the constituent atoms or molecules. So this magnetism of the material is mainly caused by the interactions of uncompensated magnetic moments. Uncompensated, the directions will be random, or the directions, the alignment will be in different directions to the applied field, like that. So the magnetism of the material is mainly due to interactions of uncompensated magnetic moments of the constituent atoms or molecules. Based on the response of the materials, based on the response of the materials in an external field, they are divided into three categories. So, magnetic materials based upon the response of external field, they are divided into three categories. So, depending upon the alignment of magnetic moments within the materials, so these are again classified into five groups. So, based upon the response of the material in an external field, so they are categorized into three. Again, depending upon the alignment of the magnetic moments, they are classified into five groups. So they are diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and then ferrimagnetic materials. Okay, so the five groups of magnetic materials, which are classified depending upon the alignment of magnetic moment, or diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic material, and then ferrimagnetic materials. So, in ferromagnetic materials, these ferromagnetic materials are further classified into two types, that is, soft materials and then hard materials. Ferromagnetic materials are furtherly classified into two types. One is soft material, another one is hard material. So these materials are widely used in the information storage devices. So these soft and hard materials are mainly used or widely used in the information storage devices. So let's see magnetism. So what is magnetism? The attracting property. The attracting property exhibited by the magnet is known as magnetism. So attracting properties that a material exhibited by the magnet is known as magnetism. Magnetic dipole, a magnet consists of north pole and south pole. So any two equal and opposite poles, any two equal and opposite poles separated by a distance constitute a magnetic dipole. Any two equal and opposite poles separated by a finite distance constitute a magnetic dipole. So this magnetic dipole produces magnetic moment depending upon the alignment with respect to the applied magnetic field. Magnetic flux. Magnetic flux. So the magnetic flux is defined as the amount of magnetic lines of forces that are passing through a point. Magnetic flux is the amount of magnetic lines of forces passing through a point. It is denoted by phi. Phi is equals to A. So the parameters in this expression, where A is area of cross section of the material. A is the area of cross section of the material, which is measured in meter square, and B is the magnetic induction. Magnetic induction, which is measured by the Weber per meter square. So the units are Webers. So magnetic flux will be measured with the units of Weber. So as we have phi is equals to area of cross section meter square, but where in the magnetic induction the units are Weber per meter square, so that phi will be calculated in Webers. So it is measured in Webers. That's why units for magnetic flux is in Weber. Intensity of magnetization. Intensity of magnetization, which is denoted with the capital M. When a material is magnetized, it develops a net magnetic moment. The magnetic moment per unit volume is called intensity of magnetization. So when a material is magnetized, it develops a net magnetic moment. So the magnetic moment per unit volume is called intensity of magnetization. So the magnetization capital M is equals to magnetic moment by volume. magnetic moment by volume. So the units for intensity of magnetization is ampere per meter. Coming to the magnetic field induction. Magnetic induction. So the magnetic induction, or we can say magnetic flux density, at any point or at a point is defined as the number of lines of force through unit area of cross section perpendicularly. It is denoted by capital B. So magnetic induction B is equal to pi by E, where A is the area of cross section of the material. So magnetic induction at a point can be defined as the number of lines of force through unit area of cross section perpendicularly it is denoted by capital B. B is equals to pi by A. Magnetizing field strength. Magnetizing field strength capital H. The magnetic field strength H at any point is the force experienced by a unit north pole placed at that point. The force experienced by a north pole, the magnetic field strength H, the magnetic field strength H at any point is the force experienced by a unit north pole placed at that point. So units for magnetizing field strength is ampere per meter. The magnetic flux density generated is proportional to the magnetic field strength. So that the magnetic induction is proportional to the magnetic flux density. So B is proportional to H. B is proportional to H, where B is the magnetic field strength and where B is the where we are saying that B is proportional to H and B is equals to mu H. So this is the relation between the magnetic flux density and then magnetic field strength. Okay, so B is the magnetic flux density. H is the magnetic field strength. So that the magnetic flux density is proportional to the magnetic field strength. Okay, so B is proportional to H. While removing this proportionality, we will have a proportionality constant. B is equals to mu H. So where here mu is the absolute permeability of the medium. Absolute permeability of the medium. If the medium is air, or else if the medium is vacuum, then the magnetic flux density B is equals to mu naught H. Mu naught H. Where B is the magnetic flux density, mu naught is the permeability of free space. Permeability of free space, and H is the magnetic field strength. So the permeability of free space mu naught, which is in air or vacuum, the value is mu naught is equals to 4 pi into 10 power minus 7 Henry per meter. This is the value for mu naught value. Magnetic susceptibility. If magnetic field strength is the applied magnetizing field intensity and M is the amount of magnetization of the material, then susceptibility can be defined as a ratio of magnetization divided by magnetic field strength. Okay, So M is the magnetization, H is the magnetic field strength. So if H is the magnetic field strength, M is the magnetization of that material. So susceptibility can be defined as psi is equals to M by H. So units, so it doesn't have units. So it has no units. Where here phi is equals to 0 in vacuum, where it is positive for paramagnetic and ferromagnetic materials, and it is negative for susceptibility is negative for diamagnetic materials. Magnetic permeability, which is denoted by mu. So the magnetic permeability is defined as, or it is the measure of the amount of magnetic lines or forces that is penetrating through a material. So the magnetic permeability mu is a measure of the amount of magnetic lines or forces that are penetrating through a material. So it is defined as the ratio of magnetic flux density or magnetic field induction strength B in the material to the applied magnetic field intensity H. So that mu is equals to B by H. So B is the magnetic field or magnetic flux density, H is the magnetic field strength. So that B by H, mu is equals to B by H. So from this, B is equals to mu H. So permeability, magnetic permeability is a measure. How much how much amount of lines of forces, magnetic lines of forces are penetrating through a material. So when expressing through mathematically, so it can be defined as a ratio of the magnetic flux density to the magnetic field strength. So mu is equals to B by H, B is equals to mu H. So there are three permeabilities, that is mu, mu naught, mu R. So the relation between these two, the magnetic permeability mu is equals to mu naught, mu R, mu naught into mu R, where mu is the absolute permeability of the medium. Mu is the absolute permeability of the medium. Mu naught is the permeability of free space, that is air or vacuum. Mu R is the relative permeability of the medium. Relative permeability of the medium. Coming to the magnetic permeability of free space. Magnetic permeability of free space mu naught. So the magnetic permeability of free space mu naught, it is a measure of the amount of magnetic lines of forces which are passing through a medium. So that medium is specifically air medium. Okay, so it is defined as the ratio of magnetic field induction strength V naught of a free space or air to the applied magnetic field strength. So that mu naught is equal to V naught by H. So where V naught is equals to mu naught H. What is this V naught? So this V naught is the magnetic induction field strength. And H is the magnetic field strength which is applied magnetic field strength. So V naught is equals to mu naught H. So where mu naught is equals to 4 pi into 10 power minus 7 Henry per meter. So now we can calculate what is the relation between the H, B and M. So that is coming to the relative magnetic permeability mu r, relative magnetic permeability mu r. So from this we are going to see the relation between B, H and then M. So magnetic field induction and magnetic field strength and then magnetization. So from this topic we are going to verify the relation between BH and M also. So coming to the relative magnetic permeability mu r, it is the ratio of permeability of a material to the permeability of free space. As we know that mu is equals to mu naught mu r. So when coming to that mu r, it is equals to mu by mu naught. So that mu r can be defined as relative permeability, can be defined as the ratio between permeability of a material to the permeability of free space. So mu is equals to mu naught mu r. So what is the relation between B, H and M? What is the relation between B, H and M? So B is the magnetic induction field strength. H is the magnetic flux density, or else we can say that magnetic induction field strength also. H is the magnetic field strength and M is the magnetization. So now we shall see the relation between B, H and M. So as we know that B is equals to mu H, and come here when substituting that mu is equals to mu naught mu r. Let it be 1. So here by substituting equation 1 in the above equation. So here mu is equals to mu naught mu r. Okay, so we know that B is equals to mu h. So where mu is equals to mu naught mu r here. So mu naught mu r h. So now B is equals to mu naught mu r h plus I'm adding mu naught h and subtracting mu naught h. So plus mu naught h minus mu naught h, and I'm writing in the form of m. So we know that m is equals to h into mu r minus 1. So that from this expression b is equals to mu naught h. So from these two terms mu r minus 1 plus mu naught h. So this h into mu r minus 1 is m. So mu naught m plus mu naught h. So B is equals to mu naught m plus mu naught h. So when taking common of mu naught, B is equals to mu naught into h plus m. Okay, so a relation, now we shall see the relation between the susceptibility and then relative permeability. So as we got in the previous expression, B is equals to mu naught into H plus M. So mu naught is equals to V by H plus M. V by H plus M. So where relative permeability, we know that mu R is equals to mu by mu naught. So what is the mu value? Mu is equals to V by H. Why V by H? So V is equals to mu H. Okay. So that V by H by V by H plus M. So where mu naught is equals to V by H plus M. So this is equals to V by H into H plus M by V. So cancel. We have H plus M by H. So this when taking simplifying this 1 plus M by H. 1 plus M by H. So that the susceptibility, it is the susceptibility. Susceptibility is nothing but M by H. That is ratio of magnetization and then magnetic field strength. So it is equals to M by H. So let's substitute mu R is equals to 1 plus M by H. It is equals to 1 plus susceptibility. So this is the relation between the relative permeability and then susceptibility. Okay, so permeability, magnetic permeability is mu is equals to mu naught mu r, mu naught mu r. So mu is the magnetic permeability, mu naught is the permeability of free space, and r mu r is the relative permeability of a relative permeability of the medium. Coming to the magnetic permeability of a free space, mu naught is equals to V naught by H. Mu naught is equals to V naught by H, where V naught is the magnetic field strength in the air and H is the magnetic field strength. So V naught is the magnetic flux density of the free space, H is the magnetic field strength. So relative magnetic permeability, mu r is equals to mu by mu naught. Mu by mu naught. So from this mu is equals to mu naught mu r. So relation between BH and M, we know that B is equals to mu H. We know that B is equals to mu H. B is equals to, instead of mu, we are replacing with mu naught mu r from this first equation. So B is equals to mu naught mu r H. So now I'm adding and I'm subtracting with mu naught H. So B is equals to mu naught mu r H plus mu naught H minus mu naught H. So let's substitute the value, the expression where M is equals to H into mu r minus 1. So that B is equals to, when taking common mu naught H, so we'll get from these two terms. So mu naught H into mu r minus 1 plus mu naught H. So from this, B is equals to mu naught M plus mu naught H. So that B is equals to mu naught H plus M. So now we shall see the relation between the susceptibility and relative permeability. So B is equals to mu naught H plus M. And we know that mu naught is equals to V by H plus M. Let's substitute that mu r is equals to mu by mu naught. So mu, we know that V by H by V by H plus M. So simplifying this, we get 1 plus M by H. So where 1 M by H is the susceptibility, so that mu r is equals to 1 plus So this is the relative variability and susceptibility relation. Next, coming to the magnetic moment or magnetic dipole moment. So the magnetic moment is the product of pole strength and then magnetic length. Pole strength and magnetic length. So magnetic moment is denoted with mu m. So that is equals to current into area of circulating orbit. So that mu m is equals to current I. Area of circulating orbit is pi r square. So that mu m is equals to I pi r square I. So units or ampere dash meter square. So when the magnetic dipoles undergo orbital motion or spin motion, it produces a magnetic moment. Since motion of charged particles is considered as closed electric current loops, this is in turn produces magnetic moment. So here we can take atoms consisting of charged particles like protons, electrons, like that. So when they are undergoes some type of motion, that is orbital motion or it may be spin motion, they produces magnetic moments. So since they are charged particles, they are in motion, so that motion of charged particles is considered as closed current loops. This is in turn produces magnetic moment. So that when the magnetic dipoles, atoms consisting of charged particles like protons and neutrons, undergo orbital motion or spin motion, produces a magnetic moment. Since motion of charged particles is considered as closed electric current loops, so that they produces magnetic moment. So these are the basic definitions which we have to know to understand the topics regarding to the magnetic properties. So the references for this topic is Engineering Physics by Tyagarajan, which is published by the McDowell Education Private Limited, New Delhi, and then textbook of Engineering Physics, and then Engineering Physics by Dr. M.R. Mukam, Engineering Physics by P.K. Palaniswamy, fourth edition, scientific publications. These are the references which I used for this magnetic properties topic. So in the next session, we shall meet with the other topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.